Okay, 2013 was one of our flagship parts, one of our original parts. What we wanted to do was there was a legacy part at a competitor known as the SBB 5089Z that we saw being used all over the place. Reason being, it was a broadband gain block that went from 100-ish to about 4,500 megahertz, flat gain, good IP3, and a compression point of around 20 dBm. So we wanted to match that or outdo that. So you designed the GRF 2013, which is a semi-equivalent. It has some advantages over the SBB 5089Z. That being, you can match it in subbands above 6 gigahertz, which we've done from time to time. You can take it down to 10 megahertz if you put in the proper hooks and get an marginally acceptable noise figure at 10 megahertz. So it can be matched. It can be matched. I have matched it broadband from 10 megahertz to 6 gigahertz with some specialized, with a specialized RF choke arrangement where I put a ferrite first in place of the choke. And then above that, I put a really big inductor to handle the VLF, the very low frequency. So it can be matched from 10 to 6 gigahertz. I just did that for a customer, and they're actually using the match. So it is our do-all, end-all broadband gain block, and it goes into varied applications. Has a good noise figure, slightly above 1. Has IP3s that are pretty darn high as 40 dBm in some places, and a compression point of 22 to 23 dBm, which just outdoes the competition. So it's best in class. We have recently designed some devices that rival it. GRF201X for the higher frequency stuff, like Chris was talking today, GRF201X, which are high frequency spins of the GRF20105, which we may discuss today, and the GRF20112. So we can give you the broadband gain block solution from, gosh, now it's 10 to 12 gigahertz in chunks between the 2013, 2105, 2110, 2111. So the 2113 was the beginning of all of it, and it'll still be the best choice in some instances. Okay, GRF 2013 comes in a DFN6. Yeah, 1.5 by 1.5. And it comes in that is a common package to a myriad of our smaller devices, which means they use the same eval board. They have pretty much the same configuration, so we can mix and match and substitute if we get a situation where we need, say, we need higher gain at 1 gigahertz. I can put a 4014 in there. I mean, I can exercise options because they're all in the same package, which helps me out a lot.
Any of you guys call me Francis, and I'll kill you.
"2013 drawbacks are sometimes you have to live with, if you do a broadband match, in order for Ryan to get the performance, the P1 and the IP3, he had to say, okay, sometimes the return loss will dip below 10 dB. That to me is the trade-off. If I match it in that match from 10 to 6 gigahertz, for instance, I had good return loss on the band edges. In the middle, it degraded, but you know what? The gain stayed pretty flat, and to be honest with you, practically speaking, that you can live with a return loss that gets worse than 10. It's not a problem. Some customers get up in arms about it. Oh, we need this return loss the whole way, when in reality they don't. It'll work just fine. So that would be the drawbacks. The return losses aren't way down in the dirt. If there's a drawback, that's it. It does really good over temperature. The whole family, 2013, 2011, 2012, 2014, they do very, very well over temperature. They retain their IP3. Compression point only degrades 1 dB. So over temperature performance is a strength. 2010 would be the lowest gain option, which is a 2013 with more feedback, therefore higher noise figure. Lower gain, like 10 to 11 dB. Same characteristics everywhere, just 10 to 11 dB a gain. 2011, 14 dB a gain, same deal. Mid-range gain, a little bit better noise figure than the 2012. 2011 and 2012 are closely related. 2011 has a half dB better noise figure, and so that's how that family goes. 2014 would be you get more linearity. You get higher IP3. Peak IP3 will flirt with with the right match in the right frequency band. Will flirt with. You'll get 44. You'll get 44 dBm. In some instances, all these are cascodes. You can all run them at higher voltages. 2014. Sometimes, depending on the frequency, you can run it at 8 volts and get a higher P1 to make it effectively a larger device. So it would be the most linear PA amplifier in that family. 2014. '23 to 24. If you run it to 8, you can get 26 to 27, depending on the frequency you're at. Stability issues, in reality, no. But what you will see, and again, what you can see, some customers get concerned with it, is the stability indices, mu, K factor, they'll go below 1, slightly below 1, and therefore you don't have unconditional stability. So sometimes I have to adjust the match to bring in unconditional stability, which I put in quotes because you can make anything oscillate if you match it wrong. All unconditional stability says is that you can make this amplifier unconditionally stable on this eval board, when in reality, if the stability indices are not, if they're decent, close to 1, I'm pretty happy with it, and I can usually explain it away. So no stability problems per se with these devices. Because like you're saying, these PHEMT devices, if there's going to be a stability problem, it's going to be at high frequency. It's going to be at high frequency. So the shunt, small value shunt capacitor, sometimes externally takes care of it. With a 2014, if I have to bring in the stability indices, that's how I do it. At the input too, sometimes. So we can usually stabilize it. Not really, except that they are going to be around. They've been around forever. They're going to be around forever, and they're always going to be, in some cases, they're going to be the go-to devices for, we sample them all the time. The good compression point, the good linearity, and the good noise figure. It goes everywhere. It can be used everywhere. So we are gonna we use them a lot, and we tune them all over the place. So they're just solid. They're just solid, and they're a foundation in our portfolio. General purpose is what we're about, and they are the building blocks for our general purpose broadband amplifier family. I think the SBBs were, I think that happened when they tried to do a follow-on family of devices. the next gen family of devices, and I think that they ran into some stability issues with them. I also remember that one thing you had to keep in mind when you cascaded these amplifiers, the S12 was such that they when you were cascading them, you had to they talked to each other, and your response got degraded, your flatness and your interstage matching between the amplifiers, which required that you put, and this is good practice anyway, it required that you put 3 dB pads in between each stage. And you know what? That's a good idea with the 2013, really. That's a good idea with any cascaded broadband amplifier, that you put pads in between them, if you can. And you should take that into account when you're doing your gain budget. I always do. Put pads in between them.
Thank you so much for watching. If you'd like more information, please email us at sales@gorilla-rf.com. And don't forget to subscribe to our channel for more content from Gorilla RF.